Welcome to the 12th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. In this video, we're going to talk about Chapter 7, which is on the simple harmonic oscillator. To the left, I'm sketching for you the wave functions of the simple harmonic oscillator put over the simple harmonic oscillator potential, which is a simple quadratic. The gray shaded region is what is called the forbidden region. You can see some of these wave functions do extend into that forbidden region, and that is an indication of how quantum particles can tunnel outside of a barrier. I also have a picture here for you of a more accurate potential that describes molecules called the Morse potential, and we are also inscribing in that the harmonic oscillator potential that fits the Morse potential at its minimum, and the horizontal lines are the energy levels of the two different potentials. If you look closely, you can see the harmonic oscillator potentials match those of the Morse potential very well initially, but then eventually they do rather poorly and don't describe the Morse potential very well. Okay, Chapter 7, the simple harmonic oscillator. This is a long chapter. There's lots of stuff in it. We start with using atomic spectra and the Leibniz rule and things like the Planck-Einstein relation and some of the notions from the Bohr model to nearly derive the canonical commutation relation. It's not a full derivation, it's more of a motivation, but it's a really close derivation, and it's motivated by experiment, so you don't have to think of the commutator of position with momentum operators is IH bar as being something that someone tells you, well, that's what works in quantum mechanics, so we're going to just postulate that that's what it is. No, it's actually motivated by experiment, and you can actually derive and get the H bar and the I just by using relatively simple arguments that motivate why and how it is the way that it is. Then we get on to discuss the free particle in full space and on a circle. When we talk about free particle on a circle, that is going to be our first problem that we're going to solve by factorization. We solve for the free particle in real space and momentum space by working with the translation operator, which is something else that we work with and derive, and by using a simplified version of what is going to become the Hadamard lemma. We then talk about how any potential that has a minimum, unless it's a very special potential, the minimum will be described near the minimum by a simple harmonic oscillator. I illustrated that for you with the Morse potential on the previous slide. We then develop the factorization method to show how to solve the harmonic oscillator. This is done very differently from the way it's done in most textbooks. And in addition, we also talk about the fact that there's a second factorization that no one will ever tell you about that also describes how to get half of the solutions of the harmonic oscillator. And it's very interesting how that second factorization works. Then we talk about the Heisenberg uncertainty principle and what it means, what it really means in terms of experiments where you're talking about the variance, and why it does not mean that in any given shot of an experiment you can't measure position and momentum at the same time, because you actually can. We then derive one of our challenging identities, the Baker-Campbell-Hausdorff formula. This is required for us to get to the wave function of the harmonic oscillator, which is the next step that we work in. We have a very nice operator-based approach to get at the wave functions for the simple harmonic oscillator. Unfortunately, this approach doesn't work for all wave functions. We have a different method that we use for the general case, but it's a really nice way of doing the harmonic oscillator wave functions. We then talk about coherent states, and then we talk about squeeze states. Squeeze states don't make it into very many curricula at the undergraduate level, but there's no reason not to. They're a little bit more challenging, but when you have the exponential disentangling identity, you can very easily work with squeeze states. We then have a chapter or a section in the chapter that we talk about the Copenhagen interpretation and what it means and how you can think about it. We also generalize the harmonic oscillator to higher dimensions, show how that works, and we look at a couple of applications of the harmonic oscillator in various different situations. All right, let's go browse through the chapter. I absolutely love this quote. It's by Joe Bennett, a journalist from New Zealand, where he said, "A while back I bought an Idiot's Guide to Quantum Mechanics, from which I learned only that I hadn't yet reached the rank of an idiot." Well, I hope those of you who have gotten this far in the book don't feel that you're an idiot and actually feel like you can comfortably learn all about quantum mechanics. So let's talk about the chapter. We start off with talking about position, momentum, and energy operators. We talk about states that have definite position, momentum, and energy. And in order to do that, we need to think about things like the kinetic energy and the potential energy. We talk about what the variance is of an operator, and that's going to be useful when we start talking about things like Heisenberg uncertainty principle. We talk about matrix elements or expectation values of operators and states. And we spend a fair amount of time describing exactly what variations mean, what variance means, because a lot of people don't really understand the concept very well. You can have things that have the same average and very different variances. Then we derive is kind of in quotes, the canonical commutation relation. It's really very strongly motivated, but we do it by using the fact that spectra and atoms have sharp lines, and the Planck-Einstein relation and the ideas from the Bohr orbit that there are stationary or stable states. And then essentially just using the Leibniz rule, we motivate very strongly what the canonical commutation relation is. It's a very nice way of thinking about it, and I really like the fact that we can motivate the canonical commutation relation via a connection to experiment. So we don't have to use an ad hoc rule like the one that Dirac came up with, that you take a Poisson bracket, which no one really understands what those are anymore, and you replace the Poisson bracket by a commutator, and you replace the 1 by an IH bar. I mean, who comes up with that stuff? Where's that come from? No, you can actually think of it very carefully in terms of the reason why we have atomic spectra means that we must have a canonical commutation relation where commutator of X operator with P operator is equal to IH bar. It's as simple as that. Okay, then in the next section we talk about the free particle. We get at deriving this by using the Hadamard lemma, and we're using tricks like multiply by 1 and things like that in order to do the derivation. We haven't yet fully derived the Hadamard lemma. We're going to get to that very soon, but we had a baby version of the Hadamard lemma that we derived when we talked about the canonical commutation relation, and that's enough to actually get the free particle position and momentum eigenstates. Then we move on to looking at free particle on a circle. This is our first experience with working with factorization. I don't try to get you to derive the way that you would do the factorization. I just tell you what it is, and we work it out and we check and verify that it works. Particle on a circle has a lot of subtlety to it, and we carefully go through all of that subtlety. We show you how you can calculate complicated commutators, like the commutator of momentum with the tangent of k times x, and so forth. And this all just follows from our Leibniz rule and very clever ways of thinking of doing the algebra. And we find that there are multiple states, and in most cases, two states share the same energy except for the ground state. And so there's lots of interesting things that come up when we talk about particle on a circle. We also learn that the position operator isn't actually a valid operator on the circle, and that's actually an interesting thing to talk about and really work out the details of exactly why that is and what it means for the quantum mechanics that you do on a circle. Okay, we have, of course, a number of problems to help reinforce how that works, and now we introduce the simple harmonic oscillator. We talk about how pretty much any potential with a minimum can be approximated by the simple harmonic oscillator. There are a couple of exceptions, like a quartic potential can't be approximated by a simple harmonic oscillator. We then talk about the operator method to find the energy eigenstates of the simple harmonic oscillator. Many of you might have learned that this came from Dirac, but that's completely wrong. It comes from these three gentlemen, Heisenberg, Born, and Jordan, and they worked it out in the context of matrix mechanics, but essentially the ideas that they use there are the ideas that we can use in order to get the energy eigenstates of the harmonic oscillator. The strategy we use is a little bit different, and we go through all the details of exactly how that works. And including getting the energy eigenstates as well as the energy eigenvalues, and also how you can calculate and manipulate different kinds of operator relationships. We then talk about the Heisenberg uncertainty relationship. There is a formal part of this where you derive an explicit relationship between expectation values of operators, and then there's a more informal or applied part of the uncertainty relation where you try to apply the uncertainty relation to different kinds of situations. And when you apply it to experiment, this is where often people get into the incorrect notion that you cannot measure position and momentum at the same time. That is incorrect. And the reason why it is often taught incorrectly is most people who teach it don't actually know how you measure momentum. You'd be surprised to learn that the most common way of measuring momentum is via time of flight, where you measure position to infer momentum. But even without that, if you're directly measuring the particle, your detector is located somewhere, so it is measuring position no matter what you're doing. So you have to really think carefully and understand how these experiments are done before you start talking about things like what you can and cannot do with momentum and position. What is always true is that a quantum state cannot have an uncertainty in position and an uncertainty in momentum that violates the uncertainty principle. And that is always true, but that is not saying anything directly about experiment. Then we talk about parity. Parity is like a mirror reflection. You take x to minus x and p to minus p and so forth. And that has some consequences for harmonic oscillator because the harmonic oscillator potential is an even potential, and that allows us to classify states in terms of parity. Then we get to a really hard derivation, the Baker-Campbell-Hausdorff formula. This is one of our more difficult derivations. It takes quite a bit of effort. I actually tell you to go through parts of it, and then I give you places where you can stop and then just trust me for the rest, or come back to it later when you're feeling more comfortable in working with operators. There's a lot to this, and it really relies on being comfortable with doing proofs by induction, being comfortable with doing some complicated algebra and so forth. It's a difficult derivation. We can't derive everything all the way through for the full formula, but really no one does that. The full formula is known, but it's known in a very complicated way that is very difficult to work out all the details of it. But there is one form of it which is called the Weyl form, which is shown in this formula, and that is a really important form of the Baker-Campbell-Hausdorff formula. That was the first part of it, and we're eventually going to get to the full Weyl form of the Baker-Campbell-Hausdorff formula, and that's the one that we use most of the time. The derivation of that is something you should certainly be able to follow, even if you cannot follow the full derivation of the Baker-Campbell-Hausdorff formula. Don't feel bad if you cannot. Just come back to it a little bit later when you feel more comfortable with doing complicated algebra. Okay, with the Baker-Campbell-Hausdorff formula, we're now ready to evaluate the harmonic oscillator wave functions themselves. And evaluating these wave functions requires us to do a number of different operator manipulations, but it's a really cool exercise, and I guarantee you've never seen it before. No matter how many quantum mechanics classes you've taken, this is completely new stuff. It was never done before. We worked it out a few years ago. Then after, and you can do it both in position space and in momentum space, you of course get the Hermite polynomials and other things like that, and you can then plot out the wave functions. I will have a plot for you. This is one of the plots that I put on the first slide for this chapter. You can look at things like what are really large n wave functions and what are their probability distributions and so forth. There's a lot of interesting stuff you can do to thinking about that. Then our next section focuses on coherent and squeeze states. These are really important for quantum information. You can't say that you're doing anything in quantum information if you don't understand what coherent and squeeze states are, especially if you're thinking about doing something with quantum sensing and quantum information. So we can work with these. Hadamard lemma and things like that get us a really far way. So we have the proof of the Hadamard lemma here. This is a picture of Kennard, who is the first person to talk about squeeze states, and then Glauber, who's the person who really worked with squeeze states. Schrödinger is the person who actually was the first one to work with coherent states. So they've been known since the 1920s. They're interesting things if you plot the average positions and average momenta in phase space. You can see what patterns they trace out. We have to use our exponential disentangling identity to do things with squeeze states, and so it takes some time to fully derive that exponential disentangling identity for the symplectic group, and then see how it's used and figure out the right way to use it when you're working on evaluating expressions with squeeze states. We can work out the wave functions of these different objects, both the coherent state and the squeeze state. And then I have a section where we talk about the Copenhagen interpretation as it's applied to the simple harmonic oscillator. This chapter has a little bit of philosophy in it, but it also has a really nice derivation where we show how you can go from a position eigenstate to a momentum eigenstate via the harmonic oscillator in squeeze states. And this then verifies that we really do have position states and momentum states, which when we first derived them, we needed to have a position state at the origin or a momentum state at the origin. And then relative to that, we could find all other position and momentum eigenstates. But here instead, what we do is we actually show the existence of those position and momentum eigenstates. So it's a very cool exercise that you can do. And there are a few textbooks that do talk about this, but it's a really small number that go into these kinds of details. This is a long section. And then we have our final, I think it's our final, or maybe we have 14 sections in this. We then talk about harmonic oscillator in higher dimensions. This is relatively easy because you just kind of repeat what you did in one dimension into the higher dimensions. But you have to be careful with your bookkeeping, and you have a couple of interesting new little quirks that come up when you get into higher dimensions, so you have to look carefully at that to be sure that you understand everything that's going on. And then our final section is looking at applications of the harmonic oscillator. These are a little bit kind of contrived applications, but it is nice to be able to work through some non-trivial applications of harmonic oscillator and get a sense of how you can work with harmonic oscillator, how you can use it for approximations and other things like that. Some of these things go into pretty intricate detail about these approximations, so I think you'll enjoy looking at these applications of the harmonic oscillator. And that's basically it for the 7th chapter on harmonic oscillator. It's a really long chapter. There's a lot to it. If you're working through this on your own, it's going to take you some time to get through it. Don't try to do it all at once. Just take your time, work carefully through it. Get through the meat of all of the interesting and important details, but don't be afraid to say, this is too much for me, I got to come back to it after I feel a little bit more comfortable working with operators and other things like that. And please always take your time to pause and think carefully about what it is that we're doing so that you understand and feel comfortable with these quantum mechanical ideas, because you have to be able to do that to really be able to master quantum mechanics. Hey guys, let's do quantum right.